Welcome to the Professor's DuBois channel. This is Professor Corey, and this video is a mini lecture based on our first lecture covering material from Chapter 5. This isn't in any way equivalent to our actual lecture, where we discuss and practice the material in much more detail. But hopefully it's still useful. Chapter 5 introduces thermodynamics. This branch of chemistry involves calculations of quantities of energy, usually in the form of heat. What makes this interesting is that thermodynamics help explain the nature of reactions. We have seen many reactions in the previous chapters, but in reality, most materials are not very reactive, and thermodynamics will help explain why. You probably noticed in lab that some reactions will feel warm if you're holding the reaction vessel, and you most likely have used a chemical cold pack. The terms exothermic and endothermic describe if a substance is giving off heat or taking in heat. We can place energy in a chemical equation to represent these types of reactions. You're most likely familiar with the two types of energy, kinetic and potential, as well as the law of conservation of energy. On the molecular level, kinetic energy is the movement of the molecules. The measurement of this energy is temperature. Potential energy is usually described as height from the floor, which is convenient in most classrooms, but in chemistry the potential energy is related to distances between electrons, atoms, and molecules. The law basically states that if something loses energy, then something else must have gained this energy. We measure energy in joules. There are other units for energy, but the most recent measurement system that is used worldwide recognizes the joule. You can convert between joules and calories using the factor provided, and I recommend finding a really old textbook and calculate every value that you can find in calories to joules, and then write your result in the book. The updated version won't get you much fortune, but it'll make someone's day better in the future. Since we're talking about heat energy in this chapter, we will be carefully tracking the flow of energy, and this requires some boundaries. The system is usually in a reaction vessel for a chemical reaction, and the flask and the other things in contact are defined as the surroundings. You can see on the left of the image that the heat energy is going from the system to the surroundings. This reaction is hot. It's exothermic. The other image represents an endothermic reaction. If you touched it, it would feel cold. This sensation is the feeling of heat leaving your body. The heat energy will move from high to low until the system and surroundings are at thermal equilibrium, which means that they're at the same temperature. The temperature definition is a good one to commit to memory. Thermal equilibrium is when objects are at equal temperature, and two objects at different temperatures will reach a thermal equilibrium if placed in contact with each other. Heat flow is really a transfer of energy in the form of heat. So it's important to realize that it is not a substance or a temperature. Heat is energy, and we will represent it with the lowercase q. Three important values that dictate the amount of energy transferred. The first is the amount of material involved. The second is the magnitude of the temperature change. This is described with a triangle symbol, which comes from the Greek alphabet, and it's called delta. When you see a delta symbol, you want to think final minus initial. We will be measuring temperature changes in this chapter, but you will likely come across the symbol in your other studies. The third value is called the specific heat capacity, and it's represented with a capital C. The units are joules per gram Kelvin. Each material has a unique value, so this property can be used in the identification of pure substances. The specific heat capacity of water will become known by memory in this chapter, but a table of values is typically provided. Worth mentioning is that water has a high value at 4.184, and the units translate to joules of energy required to raise the temperature of the substance by 1 degree Kelvin, or joules per gram Kelvin. Metals have much lower values than water. You will see specific heat capacity values in temperature units of Celsius and Kelvin. You can convert from one to the other, but in the case of the change in temperature, they are the same value. The image shows how, if we had 280 Kelvin as the final temperature and 278 as an initial, the change in temperature is 2. The same is true if the units were in Celsius. So in the event of a change in temperature, no conversions are required. If we have a single substance changing temperature, we can calculate the amount of heat using the relationship Q equals mc delta T. Depending on if the temperature increases or decreases, the result may be a positive number or a negative number. The plus or minus sign indicates the direction of the heat flow. A negative value means that heat is leaving, or it's exothermic to the system, while a positive value represents an endothermic change where the system takes in heat. Many of these calculations require a conversion to kilojoules, so you'll want to know that conversion. Just one object in this problem, and we're provided with the specific heat capacity, the mass, in both the final and initial temperature. The resulting value for Q is negative, which means that heat was leaving the copper, which makes sense since its temperature went down. When two objects are involved at different temperatures, we must realize first that heat will flow from the hotter object to the colder object until thermal equilibrium is reached. We assume that no heat is lost to the surroundings, which would require that all of the heat lost by the hotter object would be gained by the cooler object. We can represent heat energy with the lowercase q, so we can say that negative Q for the hot object equals positive Q for the cold object. The negative and positive sign represent the heat flow. Negative means heat is leaving. We can solve for Q using mc delta T, so we can use this relationship instead of Q. What we do next is move both equations to one side of the equal sign, eliminating the need for a negative sign, and setting the terms equal to 0. Heat lost plus heat gained equals 0, and this is consistent with the law of conservation of energy. Some practice using this formula will be required. Some common examples involve finding the specific heat capacity of a metal by heating it to a known temperature and placing it into a known amount of water at a known temperature. And we can also use this calculation to find the temperature at thermal equilibrium, which will be the final temperature. This is used in beer brewing, where water is heated to a certain temperature and added to the grains so that the resulting mixture is at the correct temperature to break down the starches into sugars. A sample calculation is provided in the image to the right. The metal is heated and placed in water. The specific heat of the metal is calculated as 0.469 joules per gram Kelvin. Does it make sense? It's a low value and much lower than water, so at least it's a logical answer. Thanks for watching. Please give this video a thumbs up and subscribe if you would like to see more mini lectures on the Professor's DuBois channel.